Now, is this for a proportion or a mean? Is this a confidence interval or a hypothesis test? It will typically tell you, but that is where people often struggle the most. So go ahead and do that. Proportion or mean, confidence interval, or hypothesis test. Weird. I've never had that happen, so I was like, I don't know so. That's so crazy. What happens if you click on your speaker button? It's muted. Both ways. Yeah. Yeah, I never had this problem. That's weird. I thought, all right, so seriously, one of the most important steps today is to do that. Please go ahead. Proportion, mean, pricing, corresponding symbol, those kind of things. P for proportion, what for mean? Mu, yeah, population. Oh, not that. Just the first one. I was expecting to just give me one thing. And then don't worry about it. Okay. Is that hypothesis test or confidence test? It is me, but then hypothesis test or confidence? All right, so let's see how we're going. We'll talk about that as we go through. I did want you to try first. Now, can anyone tell me what this is? Mean or proportion for that first problem? Okay, good. How do you know a mean? Because it says the word mean. Anytime it's about a mean, you will either see the word mean or average. That has to happen. Okay. Now, the first thing you need to do is not listed. The first thing you should always do in these problems is pull out your formula sheet. Now, if you're in my class, that formula sheet is right there next to you. If you were in someone else's class, the formula sheet might look different because maybe they take some things off because there's a little extra that we haven't gotten to yet. Okay, I'm going to flip over to that. And then when I flip over, that doesn't share, does it? Ugh. All right, so there's the formula sheet. Now, everything in the top part is old stuff, okay? Except for right here, what I'm highlighting. This is 7.1, sampling distribution for proportions. Notice how it says sampling distribution to sample proportion. And this is 7.2, same thing for means. Okay, so if you're taking the test and you see a problem that talks about a sampling distribution, that's a big clue to go to one of those two parts. Most of what we're talking about tonight are confidence intervals and hypothesis tests. And so for proportions, we have all of this stuff. Confidence interval first. See how it says large sample confidence interval? And then here's our sample size formula. And then here's our setup for hypothesis test. We need a test statistic for that. Okay, so for proportions, it's right here. If we want to do it for means, we go to the second page. Which my computer's sad. Okay, and again, we're only doing the part 1. Part 2 is chapter 10. So one sample, T confidence interval for a mean, right there, and then hypothesis test right here. Okay, third one. So we just talked about this problem. We said it was for a mean. Is it a confidence interval or a hypothesis test? It's a confidence interval, and we know that because it says find a confidence interval, and it gives a confidence level, right? So I'm actually right here, this first bullet point. And again, I would not do a single problem on a test without looking at the formula sheet because it tells you almost everything you need to know. Now, before we actually find the confidence interval, what's in parentheses there? Those are the assumptions or conditions, okay? If we don't meet those, our interval will not be valid. What it tells us is meaningless. And so that's always the case with these tests, with these procedures. In parentheses, we have our conditions, and you want to start by checking those. So it says simple random sample from an approximately normal population or a large simple random sample. And I think the or there makes it a little trickier. So if it's from a normal population, it can be a very small sample. If we don't know what the population distribution looks like, we need it to be bigger. Does anybody remember what number we used to say is big enough? Okay, 15 is a common number. That's one that we see a lot with proportions. With means, 30. Yeah, absolutely. We take, if it's bigger than 30, we're going to get a relatively symmetric and unimodal sampling distribution. Okay, so let's go back to the actual problem. Okay, so I want you to look at that for a second and decide, do you think the conditions are met, and what would you write? And if you have a second, go ahead and write them down. Just like you would on a test. Because what I find when I grade tests over this stuff is people get hyper-focused on the equation, and the equation is just like a little part of it, right? People don't tend to have a lot of trouble with the equation. It's, did they check their conditions at all, which might be a third of the points for that problem. Did they write down a conclusion? And if you hyper-focus on just the math, you're gonna leave some points on the table. Okay, and I'm going to say, yeah, the conditions are met. That first one, it says it's a simple random sample, and I was lazy and just wrote SRS and maybe a check mark. And then our sample size, how big is our sample here? Bigger than 30, so we're good. And that's what I would say. This is bigger than 30, so that's big enough for us, and we can keep going. Now, for the interval, that's where we look at that formula sheet again, and it gives us the structure of a confidence interval, right? And all we have to remember is, am I doing this for means or proportions? We already decided that. So it's that formula right there. And I'm just copying that down from the formula sheet. Do you have to copy it down? Not really, but it's harder to make a mistake if you have it right in front of you. Now, notice that there's a T in there and not a Z. For this class, when we're working with proportions, we're working with the T distribution. I'm sorry, when we're working with means, we're working with the T distribution. When we're working with proportions, we're working with the Z distribution. They look very similar, symmetric and unimodal. The tails are higher for the T distribution. Okay, and remember the T distribution depends on your degrees of freedom. So, can anybody tell me what I'm going to plug in for X bar? What's that? Not quite. Yes, 98.4. That is the sample mean. Good, 98.4. Now, the number you mentioned, Michaela, is also going to be very useful. So X bar is going to be 98.4 plus or minus. Let's pretend we don't have to worry about T for a second. And then S, what's S? 0.3. Very good. Yes. Standard deviation. And then lowercase n is always what? Sample size. That's right. So we put a 34 there. Now, the T, we need our calculator for. Does anyone remember what button on the calculator? That sounded very excited. Inverse T is right. Let's see if I can get my calculator here to show you. Go ahead and try to find what it is while I'm bringing up the calculator. And even though you're going to see me doing these numbers, you really should get out your calculator because one button wrong can mess things up, and we want to fix those right now if we can. So I'm going to share this screen so you can all see the buttons I push. Okay. And I go to second distribution, DISTR. That's right above variables. And we're going to pick, because it said T, inverse T. Now, what we need to know is what confidence level is this for? 96%. Yes. And so when we're drawing that picture, that 96% represents the middle 96%, right? And so the T is going to come from finding the endpoint. And so when you use that middle 96%, what's left in the two tails? 2% in each one. That's right, because 96 to 4% gets you 100, but it's split evenly between the two tails. So that's why I would put 0.02 here. Now, if you just put 2, like 2%, it's going to give you an error. So you have to remember we're using decimals. Now, then the degrees of freedom. How do I find degrees of freedom? Yes, good. Sample size minus 1. Our sample size here was 34, so we're going to use 33. Paste. And it's going to give me that number right there. Now, in general, I would recommend you take every calculation 4 decimals or more for intermediate steps. And then for the final answer, round to whatever your teacher tells you on that problem. 4 is usually pretty good. So are we okay with doing that on our calculator? If you're not, raise your hand, I'll come to you. So then I put that in my formula. And then I put those in my calculator. And hopefully you're doing that too. Can anybody tell me what the margin of error is going to be? Just to the nearest percent, what would the margin of error be when you put that in your calculator? All right, what are we getting stuck on? Or we just might want to say an answer out loud. Yeah. That's a good question. Yeah, Alana just had a great question. When you actually do that inverse T, it gives you a negative 2.1382. All we're doing is looking for the distance, number of standard errors. We can take the pause and let that out. If you didn't, we'll do something right. All right, now I know I saw it on paper, several of you did it, and look, I hit enter by accident, so I already wrote the margin of error. It's 11%. I'm sorry, it's not. Yeah, it is 11. Why did I say percent? This isn't even about proportions. It's just 0.11. All right, what did you say you got? Okay, let me take a look. Okay, that's probably what you shouldn't have it. So what I would do is constantly what you do. But I think it might be so you just want to divided by so maybe just
when you install the beginning, don't include the 98 before we do that last strike. When we add subtract.
Yeah.
So the way to look at it in the fall is instead of looking at it, I think it's going.
Yeah, so there's a lot of terms there. When we're looking at just that part in parentheses, what's that called? Standard error, that's right. And when we look at everything after the plus or minus, what's that called? Margin of error, that's exactly right. And when we look at the whole thing, that's called the confidence interval.
Yeah, oh, this is what we do. This helps people.
And the thing is, when you break something you do,
That's really good.
okay, so let's go ahead and add or subtract that. That'll give us our interval. Now, really important here. An interval is a lower bound and an upper bound. The lower number should always be on the left. If you switch those, it is wrong. Okay, smaller number first. That's very important. Now, when we're talking about a mean, there's also units, so that's something we have to take into consideration. As far as the conclusion goes, confidence intervals, the percentage we see is talking about the procedure. And so the easy way of doing these is honestly kind of memorizing a way for you to state it that works. And we'll talk a little bit about what it actually means, but I would do something like this. I'm 96% confident that the mean body temperature for all EKU students is between those two values, and I make sure I put my units on there. Now, what that 96% is actually talking about is if I were to get 100 different samples, they're going to have different values and they're going to have different intervals. This means about 96 of them I would expect to contain the true parameter, and the other 4, probably wouldn't. About. If I did it thousands and thousands of times, the procedure would capture the true value about 96% of the time. All right. So did we go wrong anywhere on there? Anybody got a number issue or calculator issue? Can I keep going? I'm going to. So if I'm going a little quick, the last two parts I put at the top of this slide because I knew you might still be working on them. My question there, is it true that the mean body temperature for all EKU students would fall into the above interval? So I found a confidence interval based on a sample, and I want to know, okay, when I use a confidence interval, I'm saying something about the population. I'm making an inference. I'm saying I'm confident that the true value is in that interval. Now, in your head, try to answer yes or no, and why. And then outside of your head, maybe say it. Do we think yes or no? Okay, so I think I'm going to make you unhappy with what I said. But I said no. The real answer is maybe. Okay, we can think of a confidence interval as a range of reasonable values. If we repeat the procedure, it's going to capture the true parameter a lot of times, 96% of times here, right? But any specific interval, we don't know. That's part of why reproducibility is so important in science. If you remember the Zener card activity we did in class, we were pretty much guaranteed to get someone who seemed like they were psychic based on that, right? And it's very similar. They weren't actually psychic. Yes. Yeah, so I think maybe. I said no, but that's really too harsh. It's really just maybe. Yeah. Now, our expectation is we think that's a range of reasonable values. And if we were trying to make an inference about the population, we're going to say we're confident the value's in there. I guess what I'm getting at here is, are we sure the parameter's in there? And the answer is no, we're not. It is or it isn't. All right, now this is one of those other problems where I said I wanted you to read it. I wanted you to write down mean or proportion, and I wanted you to write down confidence interval or hypothesis test. Okay. And seriously, one of the most common questions I get is, I don't know if this is for a mean or proportion or hypothesis test or confidence interval, and it tells me. Okay. Proportions are a little mean. Sometimes they don't use the word proportion. Means always have to use the word mean or average. Proportion will sometimes do that. Sometimes you'll have to infer it based on something out of something, or you see percentages. So I'm just going to take a quick look to see what we have. And the good news is all these papers I'm seeing have written proportion confidence interval. If you didn't, if you wrote mean, just note the word mean is nowhere in there and the word average is nowhere in there, right? So you just got to slow down and read it really carefully. Now, what I want you to do is look at your formula sheet. Find the area. Notice how I wrote conditions at the top. Show that the conditions are satisfied or not. Take like 2 minutes to do that. Okay, so really common issue when we're looking at conditions and we're talking about proportions, whether it's confidence interval or hypothesis test, is getting those mixed up because most of the time, they're very similar requirements. When we're talking about means, they're basically the same requirement. There is a distinction when we're doing the confidence interval or hypothesis test. When we're doing the confidence interval, we look in the parentheses and it says simple random sample. They all say simple random sample. And then the other condition is it big enough, right? And for this one, what does it say needs to be a certain size? It says the number of successes and the number of failures. Now, when you read that problem, how many successes are there?
118.
118. So I'd say there's 118 successes. There are how many failures? How do you figure out 83? Perfect. Everything that's not a success is a failure. Those are both way bigger than 15. So yes, it is big enough for us to get a nice symmetric unimodal sampling distribution and continue on. So let's look. That's what I would write. Now, the actual interval, I write down my formula. Now, because you all knew the conditions, I think you probably know the formula. Now, I'm going to go a little quicker this time. I'm just going to show you the formula if you hadn't found that. Now, notice the Z. It's different than a T. With the Z's, that value is actually on the formula sheet, or you can use your what is it? Z inverse if you want, or normal inverse. I can't remember what it's called. We'll look in a second. All right, I'm going to show you my calculation setup. And some of us don't have this 0.5871. Where does that 0.5871 come from? Yes. Right. Yep, succession over total, so that's the 118 divided by 201. I took that out to 4 decimal places. Now the 2.58 is rounded a lot. I use that because that's the value that's actually given on the back of the formula, right? It's a little dangerous to use the one on the formula sheet because then you get used to it. If you want to use the calculator, you can take it out as many decimals as you wanted, and then maybe you're less likely to use the z value when you want to use the t. Okay, you would use your inverse normal for that. And it would actually be like 2.576 or so. Okay. And then I put everything on the right side of my plus or minus in a calculator in a single step. So if I do it in one step, that's fewer places for me to make mistakes. And I get that. So I have about a 9% margin of error. So I subtract to get my lower bound, and I add to get my upper bound. So it looks like I've got between 49.75% and 67.67%. Now, what I want you to do again, the math part's important, but the conclusion is at least as important. So try to write out your conclusion. I'm 20% confident, blah, blah, blah. What do you think, Connor?
There's nothing going on up here.
Are you 95% confident that this is the most exciting part of your week?
It's sad, but I think it might.
Yeah, even more. Just try to write the statement. Now, I do want to make a really important point here. When we are writing a statement about a confidence interval, are we saying something about the sample, or are we saying something about the population? Yes, population, very important. We know exactly what the sample value is, right? We're making an inference about the population. So I would try to be as clear as possible that you're talking about the population here. I wrote, I am 99% confident that between 49.75% and 67.67% of all individuals taking this medication would experience relief. Any questions? Okay. All right, so it looks like we've almost got it. I'll give it another 30 seconds or so there. Oh, my daughter told me a joke while you guys are finishing this. She's 9, so don't expect anything too exciting. Why did the chicken cross the playground? To get to the other slide. I thought it was great. Have I told you all the elephant joke I read recently? Yes, I have if you're in my statistics class. It's the best. If you're not, you'll just have to be curious. All right, so here we go. Now, continuing on with that same question, I say, how large of a sample would be necessary to obtain a margin of error no greater than 0.04? Now, that type of question confuses a lot of people because they see margin of error and they're like, okay, confidence interval. And it involves a confidence interval. For some reason, one of the formulas seems invisible to most people. Do you know what it is? You look like maybe you did. Okay, I'm going to jump back to the formula sheet. Now, this is the same problem, so it's still about proportions. And if I go up to the part about proportions, this middle bullet point, everybody looks over. They see the top one, which is confidence intervals and the hypothesis test, and we all miss this one. If we have a specific margin of error that we want, we can figure out what sample size at a specific confidence level will give us that. So here, we're going to use this formula. Okay, can everyone see that on their formula sheet? Because it really likes to hide from you. All right, so I'm going to go back. Here we go. And I put that there. Now, when we're thinking about what to plug in, when we use this formula, you've seen examples where we know we don't have any idea what P is, so we're going to use 0.5. And that's typically the safest thing to use because that will give you the biggest values out. It's the most conservative. If you're pretty sure you have an idea of what P will be, and you're worried about the sample size getting too big because it's a really expensive thing to study, then you can use that. In general, 0.5 is good. So I'm going to use 0.5 for my P hat. Now, M, what am I going to use for M? Margin of error, which here is going to be what? 0.04, because it says no greater than 0.04. Now, the Z is the critical value associated with the confidence level you're using, right? And before we're using 99%, so we'll continue to use that, which was what Z value? 2.58. If you were using the table on the back of your formula sheet, you maybe did 2.576. It's in that area, depending on whether you got it in your calculator or the formula. So looks like this. Except I wrote it wrong, didn't I? What is my error here? It should be 0.04. If I put 0.4, it's going to give me a very wrong answer out. So I hope you are putting that in your calculator right now. And when you do it, for some reason, it jumped and showed you everything else on the page. You should get 1040. If you're not getting that 1040.06, you should raise your hand and I'll help you. Now, it looks like I did something stupid here. 1040.06 does not round to 1041, does it? But that is the answer. Why do I round up? Okay, that's fair. Yeah. So if you're in my group, Professor Johnson did this part and he probably told you always round up. And that's true. For these, we always want to round up. Because if you're doing a study and you end up getting a margin of error bigger than you wanted, you can't just go out and interview a few extra people to start over and then get that bigger sample size. So if we're talking about the difference of one person, just round up, right? It's just it's an extra amount of certainty. So always round that up if there's any decimal at all. Now, it's unfortunate that that next part is peeking out already because I wanted to ask you this question. And I said, besides increasing the sample size, what is another way to reduce the margin of error? So that's true. If we increase the sample size, we went from, I think, 201 to over 1,000, and we saw that would cut the margin of error in half, right? So increased sample size definitely gives you a narrower interval. The other thing you can do is decrease your confidence. The reason why that happens is it gives you a smaller critical value. When you're multiplying by a smaller number, you get a smaller margin of error, right? And so you get a narrower interval or smaller margin of error. Yeah. Another way to think of that is, I think the example I really like, because I think it gives you a picture of it instead of an equation. I need a volunteer. Okay, Connor, how old am I? Well, we're going to play the bet. Like you're at a circus or something, they can guess how old you are and what you weigh and stuff. So how old am I? Taking into account I'm very easily offended.
I think you're 37.
37. Okay, you clearly believe I'm easily offended. So how much would you be willing to bet on that?
$10.
Okay, so you're not super confident. Okay, it's not very confident. So if instead I gave you a 20-year range of values, okay?
Probably between 20 and 40.
Between 20 and 40, you're being. I appreciate the laugh there. So how much would you bet on that?
Well, after that, probably a little less, maybe.
I didn't say I was laughing.
Probably 30.
More though, right? Okay, so look at that. When he had a larger range of values, a wider interval, a bigger margin of error, that came with more confidence, right? So the reverse is true. If you're more confident, it's over a larger interval, okay? So that's two ways we can do it. Larger sample size, smaller margin of error, right? And then lower confidence, lower margin of error. So one's inversely related and one's directly related. Or, I mean, honestly, to me, I just look at the formula because I look at where sample size is and where the critical value is. Now, this one, again, you have already done this part. You decided, is it a mean or a proportion? Is it a hypothesis test or a confidence interval? Okay. And these are the problems that are the biggest amount to put out there. Okay. Now, can anyone tell me mean versus proportion here? If you printed out the worksheet before you came, I misordered them. I switched the order of 3 and 4. So this one's about a goose. You probably see a chart on it. I got rid of the chart here because I didn't have space for it. Now, is that about a proportion or a mean? Good. Yes. Confidence interval or hypothesis test? Yes. How do you know? Yes, as soon as you see the word significance level, that's a big clue that you're doing a hypothesis test. Very good. So the first thing you need to do is actually, I mean, anytime you want to look at the formula sheet, that's great. The first thing you need to do is write your null and alternative hypotheses. Okay, that is super important. So do that. Write down right now. H naught is this. HA is this. Now, if we're talking about a proportion, what symbol do we use? P. Very good. Mean, we're going to use a mean. P is for proportion. That's very good. We always know the first one is technical quality. We write P equal. And the other one could be, well, an alternative. It could be greater than, it could be less than, it could be not equal. So this part I'm going to be a little quicker on, and here's what I have. Now, for this one, I think the question was majority. What does majority mean? Yeah, more than 50%. So that's why I set the null hypothesis at 50%. And we said majority, which is more than, so that's why I set the alternative hypothesis P is greater than 50%. Then you check your conditions. Now, remember, when you're looking in your formula sheet, where are the conditions? In parentheses, right next to it. Okay, so it mentions the null hypothesis, and then right away it's conditions. Now, we know simple random samples always in those parentheses, and I hope right now you're looking at your formula sheet just like you will on the test because you want to get used to that. The more you're looking at that and going back and forth, the more likely you're going to get a very good grade. And so, is it a simple random sample? Maybe. The answer is the site I got this from, YouGov, was not super clear about their methodology. I'm not sure it is. Okay, I hope it's not. Because like 8% of people said they could take a grizzly bear in a fight, which is insane. Like, and a similar number said it for an elephant. Like, how do you even fight an elephant? All right, so conditions. Yeah, they're good. Now notice, this is the weird part. For confidence intervals, it is successes and failures, right? With a hypothesis test, it's, well, if the null hypothesis is true, how many successes and failures would we expect? So n P naught, n 1 minus P naught, right? So we're going to do 50%, and that's going to give us, oh gosh, right there in front of me, 612. They're both way bigger than 15, so we're good. Then I write down my formula for my test statistic. Where's that at? The formula sheet, the same place we've been looking, hopefully, to get our conditions. And I found my p hat. I have a question. 61% is my sample proportion. Why on earth am I doing the other stuff? Why can't I just say, yeah, 61% is bigger than 50, we're done? Are we just jumping through these other hoops for fun? I mean, clearly you're all very excited and having a great time. So that's part of it. It's because we know samples vary. Okay, if 50% was the actual proportion for the population, about half the time it's going to be less, half the time it's going to be more. It's how much less or more, and is that going to be statistically significant? That's what we're doing. So what the test statistic is doing, remember, it's the number of standard errors from the mean. And is that a lot of standard errors? Think back to the empirical rule way long ago. We also call that the 68, 95, 99.7 rule for 1, 2, and 3 standard deviations. 3 standard deviations is about 99.7% of those middle values, right? Which is almost all of them. And this is saying go out almost 8 standard errors. So that's almost all of it, right? Is there very much left in the tails? No, it's tiny. We are going to get an absolutely tiny, tiny, tiny p-value. The bigger the test statistic, the more I know that, because the further it is from 0. And so there we go. In fact, this one is, and you have to put this in your calculator right now. Second distribution, normal CDF. My left bound is the value I just found. My right bound, I use 10 to the 99th because it's really infinity. So I just pick a really big number. And then 0 for the mean and 1 for the standard deviation. You're always going to be using that for a proportion. That gives me 5.97 times 10 to the negative 15. That means 0.000, a bunch of zeros, right? And then a 6, basically. So it's tiny. I wrote wavy lines 0. So it's approximately 0 is what your book says. So super tiny. Yes, Connor.
Did you say to put the lower and the upper?
So I used the test statistic for the lower, and for the upper, I used 10 to the 99. Now, I think it would be a good idea, and I would love to see if you drew a picture. Okay, now let's see if I can do that. It's going to be mean to me, I think. Let's see if I can go to this other page and do it. Yeah, I can. Okay, so, whoa. So I'll actually show you on the next page. All right, so are we okay with getting that as our p-value? That's okay. So it's just second distribution. And that's when you green but small. Okay. Now, yeah, it is a little bit small, I'm sorry. Anybody having trouble finding that p-value? I'll help you put it in. Good. Now, the important part is you remember how we did that. You know, you use that normal inverse. The reason I actually use the normal one is because of B. You're only one for the mean and standard deviation. So, oh, it's because you're lower bound. Your lower bound should actually be the 1, right? That's your test statistic. It's a 7.717. Oh, your calculator is going to go back and correct that. It's a really big number. All right, so we're good on the p-value. So I'm actually going to flip over. I've drawn a picture of what we're looking at and what I'd love to see on your own papers. Normal distribution, t-distribution, they both kind of look the same, right? That t-distribution is actually going to be a little skinnier with higher tails, but if you got a picture like that, that's great. And remember what we're doing is the test statistic is the number of standard errors. So if it's positive, it's to the right. If it's negative, it's to the left. Why do I shade to the right here?
because the alternative hypothesis is greater than, which means to the right. Okay, most of the time, if it's a positive value, we're going to be shading to the right. If it's a negative value, we're going to be shading to the left. Okay, that's how we're typically going to see it. And so you can see that's going to be a tiny value, just thinking about what it looks like. Now, the decision stage is going to be a statement about the null hypothesis. Either you reject it or you fail to reject it. Okay, and that's based entirely on comparing the p-value to the what? P-value to the significance level, right? We use the significance level to decide whether we're calling it small or big. If it's smaller than the significance level, we say it's small. If it's bigger than the significance level, we say it's big. And remember, the little mnemonic there is, if the P is low, the null must go. That's right. So, is that P low? Whatever works. What did you say?
I said the phrase you said basically got stuck in my head, just catchy.
Which one?
Or was it, yeah, he is low, no must go.
Yeah. Okay, good. So,
That value, 5.9717 times 10 to the negative 15, is way smaller than the significance level of what? What's the significance level? Yeah, that's way smaller. So reject H naught. It has to go. Now, the conclusion is about the alternative hypothesis. Basically, every time we're going to be saying, yes, there's evidence for the alternative, or no, there's not evidence for the alternative. And the decision informs that. If H naught is gone, what's left? So we're going to say, yeah, there's evidence for this. And a really nice way of saying that is, at blank percent significance level, there is or there is not evidence for blah, 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 right? Connor's recording it for prosperity. Is it too small?
The glare.
Oh, yeah, sorry. I got nothing for that. All right, online we have a Renee and 18595. How are we doing? We got any questions? It's okay if you guys do have questions. It's even great. These people aren't talking a lot. All right, so yeah, US adults think they can take a goose, which honestly I think is probably pretty reasonable. Maybe, bear less so, right? Are we good with that? Okay, so I don't have a lot of good I have a very bad autobiographical memory, so I don't remember large parts of my childhood. One of my earliest memories is being chased by a goose. And they are monsters. They are absolute evil monsters. You love them? Fair. Like, just anytime they see your brother, they chase him? Maybe that's what it is, because I'm kind of an idiot. So maybe geese just have something like that. All right, again, mean, proportion, confidence interval, hypothesis test. You probably already wrote it. If not, do it now and find it in the formula sheet. Front page, proportion, back page, mean. Look at what the conditions are, okay? Because right now, if you can do it before I tell you, that means you're more likely to do it on the test, okay? And you're more likely to remember it if you try before I tell you. So whether you're looking online, if you're watching this recording later, or if you're listening to my annoying voice in this room right now. Oh, there's a question. Oh, Lisa just doubling down, helping me.
Oh.
So the decision.
Yeah, and also go ahead and try to write no alternative boxes, because I did damn you.
That's what I'm trying to understand.
So it actually depends on the stuff. If it says you have prior value. So you don't have to. Good, you, fantastic. So if not, equal something. Good. Now, this means, right? Use proportion. You're actually the one who told me from me earlier you used. a mean. Yeah, yeah. Okay, so set up your normal alternative, H naught, HA.
Okay.
Decision that, like, depending on what our question is asking, that could be either the null or the hypothesis.
So the decision's always about the null hypothesis. Either we reject it or we fail it. And the conclusion's always about the alternative.
Now, we're actually going to be talking about that more tomorrow.
Okay.
Okay. So here we are, and I threw up the whole problem. Okay. So what is important for you to do is to get where these are coming from. Yeah, it's a random sample. It actually tells us that. Okay. And then this part is very important. How big is the sample? It tells me the sample size is 25. Now, earlier we said we were talking about means. We said big enough to not worry about is n is equal to or greater than what number?
30.
30. That's not bigger than 30. So we can't just say, yeah, it's big enough. Okay. I said it's approximately normal. And when you look in parentheses, it said normal or large. Not big enough to call it large. Where did I pull normal from? Yes, it tells us that, let's see, what does it say? It says the sample data are approximately symmetric and unimodal with no outliers. Now, we expect a chosen sample, one that's taken randomly, to be a representative sample typically, right? Which means it's going to look like the population. And so if it's symmetric and unimodal, it's likely the population is going to be symmetric and unimodal. Symmetric and unimodal, like the normal curve, right? Plus, that's pretty close to 30, so I'm not worried about it. Combined with the fact that it's symmetric and unimodal. How far can you go down below 30? I mean, if it's normal, you can go as low as you want, right? The further away it is from normal, the more you gotta be worried about that. Okay, so you wouldn't just, what I'm saying is make sure you don't just get in the habit of checking off your conditions because they can vary. And when you're talking about a proportion, don't just say there's enough successes and failures. Say there's this many successes, there's this many failures, bigger than 15. If your sample's not big enough, say, oh, look, it says it's symmetric and unimodal. That means it's normal, so we can keep going. Now, the test statistic is right here. I got negative 1.25, and I get my p-value by using p-CDF. Now, before I use the normal CDF, right? P, notice it says P in the formula. That tells me to use the t-distribution. It's going to give us pretty similar results, but those tails are higher, so the p-values are going to be a little bigger, right? One standard deviation isn't that far out, so I expect a pretty big p-value.
11%, that's pretty big, right? Not 11%, this is a mean, so just, 0.11. Okay, now, that p-value is bigger than our significance level, isn't it? So our decision, do we reject or fail to reject our null hypothesis? Fail to reject, right? Which means for our alternative, we don't really have a strong statement. We just go, yeah, we don't really have enough evidence to conclude that. Right? So our conclusion and our decision, they're both very easy to state. For the decision, reject or fail to reject the null hypothesis. For the conclusion, there is evidence for the alternative or there's not evidence for the alternative, right? They're almost always the same, just in the context of the problem.
And then I actually write out what that conclusion means, okay? I say, at the 5% significance level, there is not sufficient evidence to conclude that the mean lifetime of lithium batteries from this company is less than 1,100 hours. If you struggle with the wording of those things, I just copy it from the problem, right? The problem's like, is there evidence for this? And you're like, yes or no. Now, for those of you who have the online packet, I apologize. I added 2 questions at the end before I came in, so you'll see them on the screen. They're not long ones, though, so they're just really easy to talk about. And I'm going to pull that over in just a minute. And if you're in here in the room, I would actually write down the command for that p-value, okay, on both of them. Not only now, so you can review it, but also on a test. So if you slip and put in a silly number, we can go, oh, they were doing the right thing. Let's, give them a point for that. You want to show what you know. Don't use anything that you know off paper. Okay, so what I really wanted to do is give you an idea of the chapter 8 and 9 stuff, because that's where people get really scared. That's all based on chapter 7, and I was going to leave that off this review at first, but I figured it wouldn't hurt to talk about 2 problems really quick about that kind of thing. Okay. Oh, I forgot that has B and C. All right, so for part B, without calculating, would a 95% confidence interval for the mean lifetime of all lithium batteries from that manufacturer contain the value of 1,100 hours? So we're saying without calculating it, so we're basing it on the hypothesis test we just did, right? And our null hypothesis was that the mean equals 1,100, right? And did we reject that or fail to reject that? We failed to reject it. In other words, it might be a reasonable value, right? And we think of the confidence interval as a range of reasonable values. So you think it's going to be in there or no? Yeah, it is, right? Had we rejected that, then no, 1,100 wouldn't be in that confidence interval. And if you don't believe me, it's good practice to go ahead and do the confidence interval as well, right? Now notice, I used a 5% significance level and a 95% confidence level. Notice how those go together? 5%, 95%. They're always going to agree. They're kind of different ways, building on the same building blocks to make inferences about the population. Okay. Now, we did a one-tailed test. Remember, there's left-tailed test, right-tailed test. Left tail is less than, greater than is right tail. Two-tail, what's the alternative for a two-tailed test? Does not equal, which means it's both tails, right? How would the p-value vary if we had just done a two-tailed test? So if that had been our alternative instead, how would it vary? It was like 11, it was like 0.11, right? Yes, that's it. Two-tailed test, twice the p-value, because it's a symmetric curve, right? So just remember that. If you have a two-tailed test, you find the p-value in the same way, and you just multiply it by 2. So it's 0.22 instead of 0.11. That's just a second, like, anytime you do one of these,
just at the end go, oh yeah, was this a two-tailed test? I better multiply that by just a quick last step. Okay, oh, really quick, p-value. What's the biggest the p-value can be? 1. Smallest is 0, right? Because it's a probability. If you get 3 for a p-value, something went wrong, fix it, right?
Good, good, good. And now, dolphins. I love this question. It's super easy, but it looks super hard. Now, let's say you have 2 aquariums in a state. I think we only have 1 here. Well, I mean, I guess we have lots of people's houses. But is Newport the only big one? Yes. Okay. So let's say, do they have dolphins there? I don't remember.
No.
No. Okay. Well, then we got to go to a different state for that. So there are 2 aquariums that have dolphins with births recorded at the larger aquarium than at the smaller one. Now, records indicate that in general, babies are equally likely to be male or female, but the gender ratio varies from season to season. Sure. I mean, if you flip a coin a different number of times, you know, it might land, if you flip it 10 times, it might land on heads 5 times, it might land on heads 6 times or 7 times or 3 times, right? Samples vary. This is asking which aquarium is more likely to report a season when over 2/3 of the dolphins born were males. In other words, large versus small, which one's more likely to give us a weird looking sample that's further away from that 50%?
That's the wrong one,
Yes, why?
because it flat out says that there's less birds than from the larger aquarium, so it's less likely to actually follow.
But what? So it is smaller, but what is that? Why does that matter? So we're looking at the proportion though,
Okay.
right? If I flip a coin 4 times, it can still land on heads 50% of the time. If I flip it 100 times, it can land on heads 50% of the time, right? It's the same thing, but the coins are dolphins, which you don't flip,
Well, dolphins.
Yes. but you don't do it.
Like, the variability, like if it was smaller, there would just be like, it wouldn't be as representative to
I think you have the exact right idea. Be careful about how you say that. Larger samples, what happens with the variability? Increases, right? Variability is lower for larger samples. It's like we talked, if you flip a coin 1,000 times, it's going to land on heads really close to 500 times, right? You flip a coin 10 times, 5, 6, that difference isn't that big. You did it 1,000 times, got 600 heads, that'd be a big deal. What's that term that we learned about? Law of large numbers. Yes, when we're talking about confidence intervals, when we have larger sample size, what happens to that margin of error? So that's related to lower variability, right? So, yes, that's the answer. Good. Okay. And then the other question is just a very quick sampling distribution question. And I want to help you with that because it should be free points if you see something like it. But if it looks unfamiliar, it's going to be really hard. Okay. Okay, so I'm going over again, but not nearly as bad as the first 2 times. Do we have that or should I pause longer? Okay. So here it is. The amount of money collected, where is this? At a snack bar at a large university has been recorded daily for the past 5 years. Now, records indicate that the mean daily amount collected is $3,650 and the standard deviation is $600. The distribution is skewed to the right due to several high volume days, including football game days. Suppose that 100 days were randomly selected from the 5 years and the average amount collected from those days was recorded. Which of the following describes the sampling distribution of the sample mean? Now, there's in there some key words. I said this means look at this part of the formula sheet, right? What are those key words? Yes, yes. What else? There was a noise over here. Was it the right noise? Yeah, sampling distribution. So remember, that's right on the front page. There are 2 little boxes. Sampling distribution of the proportion, sampling distribution of the mean, right? Which one do we want? The mean, yes, which is that second little box on your formula sheet, right? And it should look familiar because it's the foundation for what we do with hypothesis tests and confidence intervals, right? That's where that's coming from every time we do it. So give me an answer. Figure it out real quick. Take 3 minutes. Circle one of them. Now, if you are circling B or D, you are wrong. Now, B is actually talking about the distribution it tells you about in the problem. It says mean 3650 and standard deviation 600. Why on earth would you not say the same thing there? Well, this is talking about the sampling distribution. All possible samples of that same size, right? And remember, it's like comparing an individual to a group, okay? Am I shocked if I find a person walking around campus that's 6 feet tall? No, of course not. There's lots of people that are that tall, right? Would it be a little shocking to find a class average height of 6 feet tall? That would be pretty surprising, right? When we take a group of people, when we're looking at a sampling distribution, remember, it gets squeezed together, right? It gets skinnier when we're looking at that because the variability changes. That formula tells you how the variability changes. It says sigma, right, divided by the square root of n, right? So the mean is actually going to stay the same. We're going to center our distribution there, right? But the standard deviation is going to be smaller. So the answer is going to end up being A or C. Do they say the same thing? No, okay, no, okay. Yeah. Which answer is it? Hey, okay. I do have another question though. That says it's normally distributed, but the population distribution says it's skewed to the right. Why is that normally distributed? Maybe. What does that have to do with it? Why? Starts with a C. Ends with central limit theorem. Yeah, fantastic. So the central limit theorem, right, which is written about in that little box, is telling us because it's large, it's going to be normal. Okay. We could actually get it by if it's small and normal. We could have it be a very small sample size and it would still be normal, right? But it actually tells us it's skewed to the right, so we do want it to be large. And how large is the sample size here? Way bigger than 30, so that's why it's normal. You're right, 100. Good. Okay, that's it. I went over on you again. I'm sorry. Thank you all for being here. If you have any questions, I'm happy to answer them. Now during class, I'm out there. Yeah, so tomorrow morning, 9:30 to 10:30. Same on Thursday. Yeah. Yeah. And then Thursday,